Alright, it's been a while. So today we're going to look at what we call vectors along a curve. Now vectors are kind of neat because they describe the motion of a particle. Now what's really unique about vectors though is if you imagine we have a particle right here. Here's a particle. What a vector does is it takes its horizontal component and makes it different from its vertical component. So if you have a particle moving through space, we can look at it in terms of what's its position horizontally, what's its position vertically. If we take the derivative, we can get the speed or the velocity of the horizontal component independently from the velocity of the vertical component. So so we can keep horizontal and vertical independent from each other, and that's very nice for us. So here we go. We have a particle that's moving along the xy plane. So that any time the position is given by this function, x of t, y of t. So what they're giving us right here is the horizontal position, and right here the vertical position. What's neat about this, I can write this in a vector form, what we call like this. I can write this as x of t, comma, y of t. Now these little arrows at the end, those are called chevrons. So I could therefore write it as t cubed plus 4t squared, comma, t to the fourth minus t cubed. And if you're thinking, man, that looks like a point, you're exactly right. This is almost a point. Matter of fact, what you learn in pre-cal, we can kind of treat vectors almost as points. But it's directional, starting at the origin. Here's my x coordinate. Here's my y coordinate, kind of where we wind up at. So if I'm looking, what they're asking me right now to find out is the velocity vector. Now to get the velocity vector, it's neat because they're independent from each other. I take the derivative of my horizontal component and my vertical component independently from each other. So to get v of t, all I'm going to do is I take the derivative of x of t. That gives me x prime of t, y prime of t. And that's not too hard to do here. That's going to give us, what is it? 3t squared plus 8t, comma, 4t cubed minus 6t squared. There's my velocity vector. But then they want me to find the velocity when t is 1, so find v of 1. Plugging it in, we get 3 plus 8, 4 minus 6, so we get 11. Whoops, I messed up here. 11, yep, and that's negative 2. Oh, that's why I messed up. That should have been 3t squared. That should be 4 minus 3, which gives us, instead of that, 11, 1. There we go. I thought I made a mistake right there. Sorry about that. That should have been a 3t squared there. I don't know where I got 6t squared. Getting ahead of myself. Don't tell anybody. So there's my velocity vector. Now what it's telling me, horizontally it's moving at a speed of, let's say, 11 miles per hour. Vertically it's moving at a speed of 1 mile per hour. Later on we're going to determine, well, how fast is the actual particle moving, and that's going to be from our Pythagorean theorem right there. Next, to find the acceleration vector, we just take the derivative again. X double prime of t, y double prime of t. And so my acceleration vector, very easy, 6t plus 8, and I get 12t squared minus 6t. And there's my acceleration vector. They want us to find the acceleration when t is 2. Plugging it in, I get 12 plus 8, and I get, 48 minus 12 here, 48 minus 12. And if I simplify that, we get 20, 36. And what's also kind of neat about this, if you notice, the acceleration and the velocity are going in the same direction. So what does that tell us about the vector, the particle itself? That's right, we know that the particle here is speeding up in the same direction. So we can apply a lot of older material to this as well. Alright, so we have a particle that's moving along the xy plane, so here's its position vector. We want to find what we call the magnitude of the vector. This is like the actual speed of the particle itself. And that's getting to the actual speed, so we'll talk about that. So before we do that, we need our velocity vector. So to get my velocity vector, that becomes 2t plus 3, 3t squared minus 6t, and I don't give a time, so let's make up a time at t equals 1. So to find the velocity at 1, we get, what's that? 5, that's 2 plus 3, that becomes 3 minus 6, so negative 3. So there's my velocity vector. Now remember what I told you. What that's telling me is horizontally, the particle is moving at 5, let's say 5 feet per second. Vertically, it's going down at negative 3 feet per second. What we're looking for is this resultant vector right here. So if I kind of draw it out here, it's kind of hard to see there. We have x prime of t and y prime of t. What we're looking for is this resultant vector right here, which we call the magnitude of the vector. So we're looking for that magnitude, and that's easy enough to do. It's just a Pythagorean theorem. So we say that the magnitude of the vector is just the square root of x prime of t squared plus y prime of t squared. It comes from the Pythagorean theorem. That Pythagoras, he knew a lot. So to get the magnitude, therefore, all I have to do, 5 squared, which is 25, plus negative 3 squared, which becomes 9, I get the square root of 34. So this is the magnitude, or sometimes called the speed of the particle. In other words, it's the actual speed. So like I said, remember from up here, if I have a particle moving along this direction, well, let me go down here, I'm sorry. So if I have a particle here, it has a vertical velocity of 5, horizontal and vertical velocity, vertical velocity of negative 3. So we know it's going to the right and down. The actual speed is the slope of that tangent line. It's that tangent line, tangential slope, which is right here. We get from the Pythagorean theorem. Now, let's say we have a particle moving along the xy plane. We again given the x coordinate and the y coordinate. The path of the particle intersects the x-axis twice. Write, but do not evaluate. See, keyword, do not evaluate an expression that represents the distance traveled. Now, we're going to get the distance traveled in just a second. It's kind of neat how we're going to kind of solve for that. But before we need to do that, we need to find the two x-intercepts. Well, that's easy enough to do. From pre-cal, we know the x-intercepts occur where y is 0. So I take my y coordinate, 1 minus 2 sine of t, set that equal to 0. Sine of t equals 1/2, and that's easy enough to do. Pi over 6, 5 pi over 6. Now in the AP test, they're going to give you a point just for doing this. Boom, they're happy about that. Now we have to define distance. Well, back in elementary school, here's how you would define distance. It is your rate times your time. Well, we can get a little bit more specific in pre-cal and calculus by saying, let's call our rate r of t, and time our change in time. Starting to look a little familiar? Well, as delta t goes to 0, our distance becomes this, r of t dt. Now remember, this is just one itty-bitty time kind of distance right here. Okay, but we have infinitely many of them. Like if this was my curve right here, from like, let's say from A to B, and this is r of t and t. If I want to find the distance this particle travels right here, right, I have to use an integral. So we take the antiderivative of this function right here from A to B. Now, remember, this is my distance I'm traveling. Now, we've seen this before when we did arc length. Now, arc length is a little bit different in parametrics and polars in the fact that they're independent from each other. So in this case, r of t right here, that's our magnitude. So, in other words, I could write distance as from A to B, the square root of x prime of t squared plus y prime of t squared. Don't forget your dt. Now, if you go to part 2, I'll kind of explain this, how I go from here to here in a little bit more detail. But you definitely want to know this formula. So the distance this is going to travel is going to go from pi over 6 to 5 pi over 6, the square root of our derivative squared. Oh no, what's the derivative of our first one? That just becomes 4 sine of t squared, plus the derivative of 1 minus 2 sine of t is negative 2 cosine of t squared dt. And there's your answer. That's a pi. And there's your answer right there. Don't solve it. All right, our last one, write the equation of a tangent line. Now for a tangent line, we know we need a point and we need a slope. Well, to get the point, we need the value at pi over 6 for x, which is easy. Square root of 3 minus 4. The cosine of pi over 6 is root 3 over 2. That's nice. It's just negative root 3. Get the y value, same idea. I'm going to go 1 minus 2 times, that's a half, I get 0. So our point, negative root 3 comma 0. There's the point. To get the slope, remember it's change in y over change in x. Well, from parametrics, we learned that this is just going to be y prime of t over x prime of t. Well, y prime of t, very simple. It's just, it gives me negative 2 cosine of t over, this becomes positive 4 sine of t. And then you plug in the pi over 6. Just plug it in. I get negative 2. The cosine of pi over 6 is root 3 over 2 over 4. The sine is 1/2. And this cancels. On top I just get negative root 3. On bottom I just get 2. So there's our slope. So my tangent line, y minus 0, negative root 3 over 2, x plus the square root of 3. So hope you enjoy the lesson. Now, like I said, if you go to part 2, we're going to go a little bit more in detail about how we get distance traveled from velocity. Okay, it's hopefully a little bit more detail for you. Yeah, see you then. Bye-bye.